So let's go ahead and start making some observations and then throw in a few remarks here and there. What do you hear to start with? If I hum a few bars, can you tell me this tune? What if I bring the microphone over close? What are you hearing? 60 cycle and its harmonics, right? So the 60 cycle is used, that means 60 cycles per second, and we're doing alternating current then, aren't we, with something. Alternating current at 60 cycles per second. And the voltage is, where is that plugged in? Okay, it's plugged in over at the wall, so what is the RMS voltage? I heard a 120, is that right? Okay, so we have 120 volts RMS, and we're thinking, oh, okay, 120 volts, how does that compare with typical battery voltages, 1 to 10 volts? It's only a factor of 10 higher, right? Okay, then what could we do if we want to make the power lines go long distances? Instead of 120, what could we do? You might think 240, 480, on up to 13,800 volts, for example, 44 kilovolts, and also different phases on the lines. I think somebody just said 3-phase. Are you charged, do you think? What's that? 30 seconds. 30 seconds. Okay, so those power lines are way up in the air, and we talked about that a little bit. I'm going to do something on the board as soon as we finish this demonstration to show you that. So today we're going to study some effects of magnetic fields with moving charges, but in a different way than we did yesterday. We're going to see something with forces and torques like we did from yesterday, but we're also going to see how the currents are changed in wires and metals when magnetic fields change. So here's our first one to start. What did you observe? And what do we have? What happened to that can? It's imploded, right? So it got crushed. Let's, do you have another can?
Yeah.
And quickly touch it. No. Oh, is it?
Hot.
Is it?
It's hot. Yeah, it's warm.
It's warm. Right? Can you feel that? It's starting to cool down, right? There you go. Pass it around. Okay, let's get another one and take a watch here and see what we see. Yeah. So what do we have here? Right here, this is white plastic with the white wire around it, but there's a coil of wire here, okay? And down below, what does this guy look like? It looks like a battery. It's a capacitor. And up at the top, if you come look at it closely, don't do that right now. If you come look at it closely, you'll see the little ceramic insulator as standoffs there. Those are designed to keep high voltages from arcing across the tops there, which means it's charging up to a pretty good voltage. There's a little thing down here in the lower right, this little tiny black piece of iron is called a transformer. And we're going to cope with transformers. And in the middle is a switch. Remember when we had the capacitors that were stored here and we turned out the lights and somebody put the I don't remember who, somebody put the shorting wire across and made a big arc and sparked and screamed and all that. I don't remember who did that. So this is to do the same effect here in the middle. So when we throw the capacitor, there's no current in the white wires at the top. That coil has no current in it to start. And then we throw the capacitor, it makes a huge surge in current. So it goes from zero current to full current in the coil up here, making a magnetic field. But there's also a change in the magnetic field. It went from 0 to full value. And as that magnetic field is changing, the can that's inside, it's metal. And the shape of the can is a loop. So there's a loop in the can, and when the current is thrown to go from 0 up to maximum value, there's an induced effect in the wire, or in the can that's inside the wire. You guys ready? Now wait just a sec. Okay, so you guys are going to watch here and just see what you can see. I'm going to go again. Ready? Go ahead. Okay. One more. Hot?
Yeah.
Okay.
Whoa.
Pass it around. Okay, thank you very much, Ben. And unplug that sucker. Okay. Oh, look at this. We need to take a moment. We got some spinning stuff going here. Let's go. How do I do that? I think for the, yeah. If you can, sure. Sure, thanks. Okay, let's see about video, document cam. Looks like I have to do the screen to get it to go. Are you passing that can around? Isn't that pretty neat? It's almost artistic, isn't it? Okay. We're going green again, folks. Okay. All right, so let's get some volunteer to help with the description down here on what we're seeing on this demonstration. Huh? She's already helped. Lauren? Is there a Lauren? Oh.
Can I help out with the bike?
Yeah, sure. Okay, have you helped? Have you helped, sir?
Yes.
Oh, some of you have not.
This guy helped.
This guy right there. Okay, come on up. Come on up. Yeah, these guys will take good notes for you. That'll be great. Hi, I'm Roger McWilliams.
Hi, Jason.
Jason, come on down, Jason. Okay. Okay, so you can see up here on what's displayed on the screen, but it's not a very good view in some ways. So Jason, can you describe to the enthralled people what you're seeing? What do we see in the back to start with?
Battery.
A battery. We're not going to touch anything for a second just to make sure it keeps working okay. A battery. What kind of battery is it?
An energizer.
An energizer. Okay, it's a D cell and it's about 1.5 volts. No, I don't want to touch it until we're done with the description. And yes, I can push it forward, but I'm refusing to in this moment. Okay, so it's a D cell, right? 1.5 volts. And then coming out from each end of the D cell is a
Rod.
yeah,
Wire.
a wire. And let's practice the Texas accent. It's a wire.
Wire.
There you go. Okay, so now the wire's coming along, and does it go anywhere at the end? Out here at the end, it doesn't. It just stops, doesn't it?
Yeah.
So these two wires then basically are just extensions of the two end electrodes of the battery. Then in the middle, what's that black rectangle? Is it something from the movie 2001?
I don't know what that is.
It's a miniature obelisk, yes.
Oh, okay.
It's for religious purposes.
All right.
Okay, so it's a magnet.
Oh, okay.
But you don't know that at this point, do you?
No.
So at some point when I'm not looking, you're going to want to check to make sure it's a magnet. Just find out, right?
Okay.
Okay, but not now.
Okay.
Okay, now what do you see going between the two, going from here over to here? What do you see?
A spinning. I don't know.
It's a little hard to see that way, isn't it? We're going
Yeah.
to stop it and take a closer look at it in a minute. So basically these wires that run parallel away from the battery have a little dip in them at the point where this guy is spinning, and it's a piece of copper. and in the center is a coil. The copper wire is looped there and then goes over to the other side. And there are a couple dips going down in these two big long parallel wires so that this copper loop will stay there. So it's a little trough for it, and it's spinning, isn't it?
Yeah.
Spinning about how fast? This is a little harder to kind of estimate, isn't it? More than once a second.
Yeah.
Maybe 10 times a second? You think
Possible,
you think it's going 100 times a second? The answer to that, probably not. One way to compare is to listen to the frequency you're hearing and compare it with that 60 cycle hum that we just heard. And this is lower frequency, isn't it?
Yeah.
Okay, so it's not going 60 cycles, it's going less than that. So somewhere 10 cycles a second, maybe 25, somewhere in that range. Okay, let's try this. What happened?
Stop spinning.
Excellent observation. Are you guys writing down for Jason? You know what? They're sitting there going, yeah, sure. They do good notes?
Most likely, yeah.
Yeah, okay, so he doesn't know. Okay. Now what?
Start spinning again.
Yeah, do you want to do that? Just so you do a little
yeah,
participation? Sure. Okay, so you saw what I did? I went this way. I didn't push down or up. I went this way on it. Ready?
Oh, okay.
Okay, go for it.
This way.
Yeah. There, now your pet loop is doing its little trick for you too.
All right.
Right? Now let's see. It's spinning this way, right?
Yeah.
Okay, let's try changing the direction of the battery. So we're going to reverse it. What do you think is going to happen?
Go the other way.
Did it go the other way?
I think so.
Yeah, it did, didn't it? Uh-oh. Okay, so we have a combination of a magnetic field and current passing through this loop, causing something in that loop. Oh, let's see. Somebody wanted it pushed forward so we could see the... How's that? Oh, somebody has the projector upside down. Let's see. Now check your direction. Can you tell the rotation direction? Okay, now I'm going to reverse it. Attempt to reverse it. Okay. What is this thing called? Anybody know?
Electromagnetic.
It's almost getting close. It's called an electric motor. You ever used an electric motor before? Okay, that's what this guy is. Jason, was that exciting?
Yeah.
What about this one? You think it'll do it too?
Sure.
Why
yeah.
not? Oh, here.
not?
You wanted to touch that? Now you've touched it. Okay, let's try putting this guy in. I don't know if this guy will work or not. Nope. And if you wreck it with the balance, almost. If you wreck, well. So motors have some delicate elements to them sometimes, and that one's delicacy has been reduced. Okay, enough for that. Are you excited?
Yeah.
He's weird. Okay, so I'm excited actually, yes, for that. That is a stunning thing. What that's saying is that if we take electric currents and run them through loops where there's a magnetic field nearby, if there's a changing flux in the loop, somehow we get this rotation going. So we are doing something with changing magnetic fluxes. Okay, let's, you want to stick around and help with the second demo? Sure, why not? Why not? Okay, so let's see. Have you helped? Have you helped? Have you helped? Have you helped? Have you gals all helped? You've helped, yes? Have you helped? Madam, your turn. How's that? Pretty fun, huh? Hi, I'm Roger McWilliams.
Aaron.
Aaron, hi. This is Jason, is that right? Yeah. I got it right? Okay. Okay. Aaron, come on over here. So, take a look at this and describe what it is.
It's a whole bunch of coils wrapped around a plastic.
A bunch of coils wrapped around a plastic holder. So it's just a spool,
Yeah.
like thread on a spool, right? And then what do we have coming out here?
There's duct tape wrapped around it, and then you have 2 alligator clamps attached to the scale.
Mm-hmm. You see why they're called alligators?
Yeah.
Okay. We don't have crocodile clamps. They're just alligators. Okay, so now it goes over here to this thing, right?
Yeah.
Okay. How many coils are here?
A lot.
Yeah.
3250.
And on what basis did you arrive at 3,250 turns?
There's a label.
There's a label. Now, at the same time now, that's a quick assessment, right? That there's 3,250. But what do we say in physics? Trust no one, right? Let's do a measurement and take a look. Look at that. Okay. How far across what's the diameter of each of the wires?
2-3 microns.
Okay, I'm seeing a diameter, it looks to me like about 0.5 millimeter, somewhere around there, so 500 microns for the diameter. And, you know, in physics, if you're nervous and don't understand stuff, you know what the best thing to do with your hands is? Exactly what you're doing, right? Then they don't reach out and touch something and kill you, right? So that's a smart thing to do. Jason, show smart position, cross arms. Now you're safe too. You're next to the dangerous stuff. Okay, so it's about 0.5 millimeter across. What's the length here? How many, put a finger in there and say, how many fingers across is that?
7.
7, 8, 9, 10. It's about 10, right? 10 centimeters, somewhere like that. And how thick is how many turns are piled on top of each other? Quite a few, right?
Yeah, like a centimeter, 2 centimeters.
1 to 2 centimeters. So you should be able to calculate how many turns there are, right? I'm not going to ask you to on your feet up here. And so you got maybe 20 to 30 turns across this way, and you got quite a few down this way. So you'll get up there to quite a few turns. And it's made of copper, but does it look exactly like bare copper to you?
No, it looks shinier.
It's got a shiny nature to it. It has some varnish on it so that it's insulated with a very thin insulation layer. And that allows the electrical current to flow along the wire but not jump from coil to coil in here, so they can be next to each other, very closely packed, but still not have any short between the coils that goes in one, goes 3,250 turns and comes out the other. Okay, Jason, what do you have in your hand?
Metal rods.
Okay, metal rods, how many? 4 metal rods. Okay, do you suppose they're magnetic or non-magnetic?
Magnetic.
How would you suppose that?
They're labeled with N and S.
Okay, makes a good start, right? And do we see a metal nearby? See if they stick.
Yeah.
They do. So they're magnetic, okay? Now, let's imagine oh, you didn't check to see if that's magnetic. At the end, do that. Or do it right now while I put the screen up.
Oh.
But that's magnets, so you don't know. Check that guy separately over at the table. Is it a magnet?
Yeah.
Yeah, okay. There you go. Here we get off. That didn't solve that. Okay, so what we're going to do is have,
Aaron.
Aaron, thank you. Completely passed by. Okay, so Aaron, you're going to hold the coil. All right, you got it? And hold on the outside. Hold on the outside. Okay, now Jason, uh-oh, the wiring's coming off. We'll have an unwanted result if that's the case. Okay, so hold it like that. And you guys, I want you to observe Jason, Aaron, and in here in the middle. Okay, this arrow is going to tell us some things. Bring that like that. Okay, now Jason, the magnetic field on these coils that Jason, or the magnets that Jason is holding. He's got the magnet, and the magnetic field is coming out like this, right? Out the end, and the other end as well, going in one end, right? So on a larger scale, if you look at it, the magnetic fields are doing this and are weaker further out, right? So they're going in and coming out. So the magnetic field strength is stronger here and weaker over here. So as Jason approaches the coil, go ahead, approach the coil. Okay, go ahead. With the magnet. So I want you to stand back, stand right here, stand right there. Now, push the magnet into the coil. Go ahead. What happened with the needles here? Okay, pull it out. Now what happened? Oh, yes. All the things you're thinking are going on here. Go ahead, do it again. Go ahead, pull it out. Okay, now, fast. Now, okay, now let's try to figure some things out here. What we have is changing is the flux, the magnetic flux that's in the coil is changing. So is the sense of humor in the class, right? Okay, so the magnetic flux in the coil is changing. Does it depend on the speed that the magnet approaches and goes into the coil? Okay, go very slowly in and come to a halt. When the speed is 0, what's the change on the needle here? Okay, now pull out slowly, very slowly. Very little change, right?
Yeah.
Okay, now go with a faster speed in and come to a halt, but faster speed. Okay, out with a faster speed. Okay, now quickly. That's about the same as last. Yeah, you got to watch what you're doing. You can't miss. Okay? So what we're seeing is this arrow over here is showing a current. The bigger this arrow is deflected from the vertical, the larger the current that is induced in the wire in the coil. Okay? Let's go really fast speed. Okay? Now if we got really fast, the mass of the needle and stuff like that makes it so we don't really see the response. So what we're seeing is as Jason brings the magnet towards the coil, towards Aaron, what's happening to the magnetic flux through the coil on Aaron's side? It's increasing as he's bringing it in, right? It's changing. The magnitude of the flux is changing. Go in with that again. Ready? Okay, go. Just go in. Okay, and so going in with it that way caused the needle to deflect to your right. Pull it back out. Pulling out caused the needle to deflect to your left. Now, reverse the magnet direction. Now go in. Whoa! You can have it both ways. Right? Isn't that cool?
Yeah.
Yes. Okay. So set it down. And thank you very much, Jason. Aaron, thank you very much for the help. So what we just observed there was that time-changing magnetic flux induced currents in the coil. And for those of you who couldn't see it very well over here because people were blocking, come up at the end of the lecture and try it for yourself, okay? All right? I recommend it. Everybody give it a shot. It's really fun, okay? So what we just saw was time-changing magnetic flux. time changing magnetic flux induces currents in conductors. Now, these cans had the same thing going on with them. Who would like this? There's another one up there. Who wants that one? Throw it on down here. See if somebody wants it. Yeah, give it a shot. Little wake-up call there. Who wants it? Did you want it, Josh? There you go. Okay. So we induced a current in both of those cases. And what we saw was increasing the speed that Jason brought the magnet into the coil, increasing the speed caused a larger current to be induced in the coil. So it's proportional to the induced voltage is proportional to this change in magnetic flux. And this magnetic flux is this B dot dA over some area. So if we want to think about the total magnetic flux in this coil, now we have to think about a couple of things. The area of the coil and what the magnetic field would be like everywhere at the coil. And then how many turns of the coil do we have? 3,250. So whatever flux effect there was on one turn gets magnified now by whatever the result is on all the other coils, all added up together. So we can do a flux for magnetic flux and do an integral over some area to determine what that total flux is. And then the voltage that's induced. Now, I just wrote a proportional there, didn't I? What happens is nature opposes change in a sense. And so the electric field that drives the current, there's a voltage then across this thing, and that's going to drive the current so as to oppose the change. So when you finish out and do the equation very carefully, you put a minus sign right in front to indicate the opposition, the natural opposition to the changing flux. So if the flux was increasing, then the current will flow to oppose the increase in the flux. If the flux was decreasing, the current will flow the opposite direction. Hence, when Jason turned the magnet around, the magnetic field was pointing one way, so going in was increasing the flux, and if we turned it around, the magnetic field was going the other way, so that the flux was changing also, but with the opposite sense. Yes?
Is that basically what happened yesterday with the 2 sheets of aluminum foil?
The 2 sheets of aluminum foil, oh, here's the way to think along that line. The 2 sheets of the aluminum foil, one sheet coming down, let's have this arm be one sheet. If the current's going down, it's making a magnetic field that looks like that. Then if the current's going down over here, you have a V cross into a B, and so you'll get a repulsion or an attraction if you think about it microscopically. So let's think here the same way. If nature is trying to oppose the change in flux, you take your hand and figure out, oh, it goes around in a circle like this. If the current's that way, it'll make the flux go through the center of the loop in this direction. And then you say, okay, that's how you decide. Think about it microscopically, which way the current needs to flow in the coil to oppose the change. And that gives you the direction of the current flow.
Professor,
Yes?
why is it that when the current's going in the same direction that the forces...
Okay, so let's make a drawing for that. If we have a wire that's straight like this and it has a magnetic field going around it, then the magnetic field is going in a circular pattern, we think, oh, what's the magnetic field? We go, oh, integral B dot dl mu naught I enclosed, right? So it says that the magnetic field that we're created is mu naught, how far around one circle? 2 pi r, and I enclosed. So the magnetic field falls off as 1 over r around the wire, and if the current's going up, the magnetic field is into the board here and out of the board over here. Now, that means the magnetic field from this wire is into the board here. This current going up also. That means a positive charge is flowing this direction, upward. And the force on the wire, the force is QV cross B. Current's going that way. It means the velocity for a positive charge is upward. Upward direction for V, crossed into B, which is into the board from the other wire, is this way. So the force is attractive if the currents are in the same direction. You don't have to remember that. You just have to remember the Lorentz force law and Ampere's law. And then it tells you, nature talks to you and says it's got to be attractive. And if you did it macroscopically instead of QV cross B, you have IL cross B, same thing, right? The L is pointing up in the direction of current, so L cross B is to the left. Yeah, that's the right way. You got it. Bingo. Okay? Did that answer your question? Okay. And I think yours a little more, right? Okay, while we're on the wires thing, let's finish off the high voltage. Why, just a little more detail about why we use AC instead of DC. For wire transmissions, we had this observation that the poles hold the wire in the air above the ground, and we went to all that trouble, all the expense of building these poles. And the reason is that we're carrying the current up here, and it's an AC current. Why did we choose AC? And the reason for that, I said, was let's look at the power consumption, right? The power delivered over at the load is going to be the V squared over R of the load, which is I at the load times V. Let's see, do we want to do and I squared R. And that's R of the load. And then we said, oh, there's also resistance along the line as it goes. So let's think about this. If we want to have a very high power delivered to the load, getting a very big voltage is a good thing because it allows us to deliver a large power at the load. So a good V squared at the load is a good thing. So high voltage would be desirable to be able to deliver lots of power there. But we also have then in the wire, there's a little bit of loss, right? In the wire. It's got conduction capability also. And you go, oh, but the wire, it's a good conductor. So it has a very little R. And if you look at V squared over R, if you have a little tiny R, doesn't the power go way high? And the answer is no. So you have to think about the physics of what's going on. This is the descriptive of the power that can be delivered to this load. When we take a charge and move it up in potential, we change its potential energy and possibly accelerate the charge to a different speed. This is when the power is being dissipated in the resistor. So as we're going along here, the total voltage across the line is not the voltage that's acting to dissipate the power here in the wire. The power that's getting dissipated in the wire is just incremental little voltage drops due to the resistance in the wire. So we can run the potential up to, say, well, let's say 13,001 volts here, and maybe only lose 1 volt going down the whole line, and we got 13,000 volts here. The voltage that's applying to the loss here is only going to be that 1 volt. We don't have the full 13,000 volts causing that loss. So the higher you can get the total voltage on here, the more power you can deliver to the load at the end. You can't, 100 years ago you couldn't make very high DC voltages conveniently. So they had to have the lines could only be less than a mile approximately to be effective. But you could make high AC voltages. And that's what I'm saying. That's why Tesla and Westinghouse were the winners in the contest, and Edison was thumbs down. So Edison got shoved out of the electric business, but what did he do instead? He invented the movie industry. He invented the moving picture camera. Okay, so he did just fine. He continued to be very inventive after that. Okay, so I just wanted to make sure, because last time I was thinking after the lecture, oh, we had this thing sitting up here, and if anybody thought about the little resistance, they'd go, oh, that doesn't make sense. Well, it does, but you have to let the physics guide your thoughts. So you could think here about, maybe you want to think the power loss here is going to be the current that's going down the line. That's the number of charge carriers per second that are going along. And then they're going to have a little bit of a drop voltage along the line. So it's the same kind of Joule loss and Joule equations, but it's not the same voltage that's acting. Okay? So nowadays, there are DC power lines. Southern California Edison uses them. And I asked a guy who ran Southern California Edison for decades, I asked him yesterday afternoon, I said, where do you use DC lines now? I said, do you use any to run out to Catalina? Because when they're underground, DC is more efficient than AC in some applications. And he says, no, Catalina has their own generating station. So apparently taking a ship with the petroleum in it over to Catalina and then putting it into the generating station there is more efficient. He said there is an underground DC line that has a terminus up at the 5 and 405, but he didn't know where it came from. So he only knew one end of the line. So it is now possible to make DC at high voltages, and so people do, but it's not quite as economically useful as some AC is for most things. Okay, let's do a little more observation then about time changing. Okay, so let's see, we had demo. Sir, oh, you've helped. You've helped? Have you helped? You've helped. Have all three of you helped? You have now? Jason, thank you very much. Okay. Have you helped? Have you helped?
No.
Your turn then. You're up. You're up. Good morning.
Hi.
Hi, I'm Roger McWilliams.
Kevin.
Kevin, pleasure. Come on around on this side, Kevin. Let's play with coils and things. So let's see. What do you see here? What's that guy?
It's just a metal loop.
Metal loop.
Aluminum, maybe.
Aluminum. And how does it differ from that one?
This one's got an opening.
Yes? So this
Not
one
close.
is a complete coil, a complete loop, an annulus, I guess you would say. And this one is an annulus, but it has a slit cut through it. So a current could not flow all the way around that guy, right?
Mm-hmm.
How about this guy?
This looks like it's brass. It's closed loop.
Okay, it looks brass-like, or copper.
Maybe copper.
Okay. And what's this guy look like?
It's a bunch of wire that's been covered in something, in a coil.
And what's that guy look like?
A little light.
A little light bulb. Okay, cool. And then what do we see here?
Looks like a bunch of metal poles with a coil wrapped around it in a tower.
Okay, and a bunch of iron. So iron has the ability to kind of help guide the direction of magnetic fields, kind of soaks into the iron and helps carry the direction. So sometimes we use iron to be the sort of equivalent of a wire. A wire will help carry the current, an iron piece will help carry the magnetic field. So, and then we got coils here, right? And then what's this guy? Yeah, have you ever seen that before?
No.
Okay, so I know you're holding back. It's called a variac. Variac, variable AC. Variac, variable AC voltage is what it can provide. And there's a button. Let's push the button. What the heck? Nothing happened, huh?
Mm-hmm.
Okay, let's try. Now push the button. Oh, that's enough. Okay, and now push the button. Okay, so this is how you find out how things work in physics. You go around and push buttons and throw switches and see what happens. Okay, so apparently this guy was off. Now we have to turn it back on. Mm-hmm. And then this guy can be over here. Okay, take that coil. All right, push the button. Okay, what happened?
Nothing.
That's a good observation. Nothing. Okay, now let's put it over here. Okay, now push the button. What happened?
Light turned.
The light turned on. Okay, go ahead, push the button. Keep going. Okay. So as long as this is down where the magnetic flux is changed. Oh, let's go ahead and do it here. Oh, not much, huh? Okay, one more. Stop. Here. Good, stop. So we need the changing magnetic flux to be inside the coil, right? It's the flux that's enclosed in the area surrounded by the coil. As I took it up here, the dipole field falls off and not much flux changing. The frequency, what'd that sound like? 60 cycles, same as that transformer? Kind of in the same ballpark? About the same, maybe exactly the same, right? Different harmonics because the structure of this thing's a little different. So what we found then, again, changing magnetic flux for sure is driving current because current is what lights the light bulb. That heated the light bulb up, caused it to emit black body radiation, and we saw the light bulb lit up, so we know there's current. Now we've proved it. What makes electric currents?
Charges
Moving charges.
Moving charges. What moves charges? What's the force law? F equals dp dt, right? And in electric and magnetic forces, what's the Lorentz law? F equals QE plus QV cross B. Q times E. Electric fields push electric charges, right? So that means there's an electric field in this wire when the magnetic flux is changing. So now we have decided not just that there's an induced voltage, but there's an electric field for sure because we know we're driving currents. Not just a voltage, but an electric field. So there's a gradient in the voltage as well. Oh, the excitement, the excitement. Let's try this guy.
All right.
You hold that guy. Okay, what temperature is it?
Room temperature. It's
And
pretty
if
cool.
it got hot to burn you, would you let go of it?
Yes,
How soon?
immediately.
Before it burned you?
Yes.
Before. Okay. Hold it over here. And hold it. And let go when it gets too hot.
Mm-hmm.
Don't be manly. Ready?
Mm-hmm.
Is it warm?
It's warm, yeah.
Got hot, didn't it?
Yeah.
Okay, so there is enough current being generated. That's pretty substantial current to take a piece of copper like that and heat it up in 3 seconds
2 or 3 seconds.
to be hot enough that Kevin said, hey, I'm out of here, right? Now, didn't we do some thermodynamics? Oh, don't say that, he said. Let's see, delta Q equals Cm delta T. dq dt equals the rate at which the heat is entering, the power is generated. Sounds like a great exam problem, doesn't it? Should we do that on the test?
Maybe.
Kevin's not on your side, folks. I said, should we do it on the test? And he should, what should he have done? A resounding no, and he said maybe. All right. What do you think? Would you like to see it on the test?
Probably not.
Probably not. Okay. All right, let's go with, now this guy's cooled down enough. Okay. Go ahead and, oh, sorry. Let's, oh, beautiful resonance. Okay, let's go, put this guy on there.
Hold
Okay.
it.
No, just put it on there. Okay, push the button. That's the right reaction. Good for you. Let's see if we can get that whole thing again. You ready? Wait. Are you ready?
Yes.
Yeah, do it again. That was great. Ready? Yeah. See, the spontaneous is a little better, huh? Okay, how high did it go? I don't see pencils writing things down. You should be making drawings.
Is that the closed?
This is, which one is it, Kevin?
Closed loop.
Closed loop, piece of aluminum, and he's holding it. How heavy is it?
10, 15 grams, maybe.
He's saying 10 grams. What do you think?
We don't trust them.
That's the right thing. You don't trust him. I don't think I have 10 bills in there. So 10 grams, and how high did it go?
Meter.
A meter. What's the change in potential energy? Right? What's the power delivered to it? How long is it in contact with the flux? If the flux is about this far, how long is it there? Go ahead, give her a shot.
2 seconds.
Get your delta T there so you can figure what the power delivery was to this guy, right? It's accelerating it. All right? Let's try this one. That one is now the one with the slit.
Yes.
The current cannot flow around the loop.
No.
But it could flow to one side versus the other, and then all the voltage could concentrate across there. If it was big enough, it would arc, but it's a big slit, so it isn't going to arc. Go ahead. Dull. Nothing happened, right? And let's take a, here, you hold that guy.
All right.
You ready?
Mhm.
Tell me when it gets hot.
It's not changing temperature.
Because current is not flowing, so there's no joule heating, right? Okay, this one's fun. You want to do it?
Sure.
Why not? What temperature is this aluminum? Room temp. Okay, put it down in there without dropping it. Okay, and you don't touch up here. Just put it down in there. Let's cool it down. You got to go vertical. It won't go that angle. There you go. We're putting it into liquid nitrogen. What's the temperature for liquid nitrogen?
77.
Yeah, it's about a quarter of room temperature, right? 77 Kelvin, somewhere in that ballpark, about a quarter. So we're cooling the aluminum ring. So as the aluminum ring cools, we know there's going to be a little bit of thermal contraction, but probably not much. The ring's not going to disappear, but maybe its resistance changes. Okay? What's the Hamlet line? No, Macbeth. Cauldron, bubble, cauldron, boil. Boil, boil. Out, damn spot. Something like that, right? Okay. Okay. Go ahead. Put it on there and flip the switch. But don't catch the ring. Okay? Are we ready? Go ahead. Who put the schlemazel in that one, huh? Okay. You want to do it again?
Sure.
No, not that good today. Okay, what happened?
Shot up higher.
It shot up by how high? 5 meters versus 1 meter? So 5 times. Oh, that means that the current in the coil must have been quite a bit bigger, right?
Or the resistance went down.
What's that?
Or the resistance was reduced.
The resistance is reduced. The voltage that's induced around the loop is the same, but the resistance is reduced, causing the current to be much larger, causing the resultant force upward to be much bigger. And you could then use your Newtonian mechanics to see how much bigger the current was, because now it's accelerated much more greatly. The time it's down here isn't 0.2 seconds anymore. It's less, isn't it? So you could do a calculation using physics 3A, using your thermodynamics, and using your electricity and magnetism. Doesn't that sound like we should just write the entire final exam on this one problem? Kevin, should we do that?
No.
Now he's thinking it through a little more and says, not a chance, bud. Okay, thank you very much, Kevin. Appreciate the help on that demo. Okay. Now, let's see. You've helped already. Let's see, we got back to Aaron. Have you helped yet, madam? You have? Have you helped? Yeah, you've helped. Have you helped? Would you like to now? Okay, cool. And then who was going to be the bike rider? Somebody wanted to ride bike. Okay. Okay, so you are?
Jenny?
Jenny? Hi, Roger
Hi,
McWilliams.
nice to
Come on over here. Okay. What is this?
It's a light bulb, really small light bulb.
And you paid for a university course to say that. Uh-oh, now we lost the lead. Okay, let's wire it up. Okay, let's wire the, okay? Now, if I, what happens?
Nothing.
Right. Okay, now let's see what happens.
Our light's out.
You're making good observations, right?
It light up again.
Now I'm going to go the other direction. Okay, really fast and really slow. Okay, and okay, that's just here's an electric power plant, isn't it? And what is this? This is the wires coming out, transmitting the power over here, isn't it? So what we have inside here is a coil and some magnets, and then as you turn that, it causes the flux through the coil to change. Go ahead. Which allows the change in EMF around the loop to include this and makes the light bulb light up at a distance. So you're San Onofre. You know the power station? Saint Onofre, right? Okay. And then the wire, the power line's coming to wherever we're using them. Okay, this was then generated by a number of people, but the most prominent in my mind is Michael Faraday. In about 1830, somewhere around there, people started figuring out that this time-changing magnetic flux could induce a current in a wire. And by 1880s, people figured out how to make light bulbs that would last more than a few seconds. And people have never looked back. So this ability to generate, we used on the first demonstration on the overhead projector, we used the electric current to rotate the coil. We made an electric motor. Now we're doing exactly the opposite. We're doing mechanical work. Jenny, is that right?
Yes.
Jenny is the mechanical work to make electricity. Go ahead. Good. So it does it both ways. this flux equation, Faraday's law, as I'm going to write it in just a minute, allows us to make electricity from mechanical energy or to do mechanical work from electricity. Motors and generators are the same thing in essence, just working in opposite ways. Was that exciting?
Yes.
It is, it is. Thank you very
Okay.
much. Okay. You're up. Now, Jenny, why don't you grab your notes and come down here? And you are?
I'm Lauren.
Lauren? Hi, Lauren. Roger McWilliams.
Nice to meet
You're
you.
going to be the bicyclist, right? Because you thought that would be cool. And I do as well. And then, let's see. Can you get on there okay?
I think so.
And we want you to put your feet into those, the foot holders in there so that you, okay, and let's see. I don't want this to get caught on the chain, so let's put it over here for a second. Okay. All right, so now, Jenny, your work will be, we'll put you here. Okay. Okay, so now have a seat, have a seat. And you're going to make some power, I think. Why don't you just pedal a little, get comfortable with it. Not too hard, okay? Just because I don't want you to slip or anything like that. Okay, so let's take a look. Let's do, okay, that's a 100-watt bulb. Oh, Jenny, let's put you a little bit further back so they can see better. You're going to be right here. Okay, now, Lauren is the source of power, right? Are you feeling powerful?
Yes.
Yes, you're right. She is the source of all power. So Lauren is the source of all power. And what I want Jenny to do is, I want Jenny to imagine that it's in the evening. And now Lauren is going to provide the power to do your homework. You need light, don't you, Jenny?
Yes.
Okay, Lauren, provide light. You need a little more, don't you?
Yeah, I see.
Well, let's use these guys. Okay, how long do you think you want to use the light?
For a while.
For a while. Are you able to take good notes about this observation? Why don't you start writing down what you see? We've got a generator over here, a very patient generator over here, right? And she's making power to provide the lights for you to work in the evening. Is this as bright as you normally like to have for your study lights?
No.
No? Lauren, you're not worthy in this moment. Let's see. No, no. Okay, let's see if you can do 100 watts. Is that not quite, right? That's more like about 30 or 40 watts. That bulb's got to get brighter to be 100. Can you do it or not?
Maybe.
Maybe, okay. But not for very long, huh? Are you getting tired?
Yes.
Okay, so just stay there a second. Don't get off till I get the lights back on here. That way, if anybody trips in the dark, it'll be me. Okay, here we go. Okay, so Lauren, you can hop off. You've done an excellent job so far. Okay, so Jenny, you can go on back up too. Thank you. Okay, so have a seat, Lauren. Excellent. Lauren is the source of all power this morning. Okay, so okay, some guy who's feeling studly. Anybody? Oh, you guys. Who have you? Oh, he's swimming in here, and you're going. Oh. Have you done it?
I already helped before.
Oh, see, do I trust him? You've helped, right?
No.
Come on up. Let's see. Lauren, now you felt what 50 to 100 watts takes to produce from your body's energy, right? From the effort you had to do. Would you do that all day long? No, not a chance, huh? Okay, and you are?
Hassan.
Hassan? All right, come on up here, Hassan. I'll get you on here. Same way, put your feet in the little pedal holders there. You're okay that way if you want. Let me check something here. I'm not seeing a, okay. Let's go slowly around. I want to make sure your pant leg doesn't catch on the gear teeth. Yeah, it's a little risky. No. Is there a clip over there, or do you know, the little bike clip for the legs? Okay. I don't want your leg to catch on the gear, so we're going to go a couple times around like that, just give you a shot. Go ahead. Okay, give us a serious pump just for a second. That's maybe 300 watts. It's not so easy, is it? No. Okay. Why don't you come on off? I'm just getting nervous about that pant leg. Let me find another guy who doesn't have a pant leg that's going to cause a problem. Oh, ah, those will probably work. You want to give it a try?
Sure.
Why not? You'll never forget it because it's a body sense that'll work. Okay, Hassan, that's good enough for you. I think. Oh, he's got a rope to. Do you want to try for more power, or do you want to let the next guy do it?
I'll let him do it, I guess.
Come on now. Let's check his pant leg too. I think yours are a little closer to the ankle so that they're less likely to catch. Okay, hi, I'm Roger McWilliams.
Nicholas.
Nicholas, hi there. Okay, hop on up and let's see if this will work. Okay, so just go around a little and see how it feels. Okay, and see if you can, see how bright you can get it to go. Yeah, maybe 300, right? Okay, hang on a sec. Let's make it so just one bulb, and you guys say when Nicholas has got 100 watts coming. Is that about it? Somewhere right around there? Okay. He's able to spin it faster, which makes it a little harder. So he's a little over 100 watts there, I think. Okay, good. All right. Did you feel the difference?
No.
Okay, let's do this. Now you can feel what it's like with none of them. Okay, and now I'm going to turn them on, and you just get it going at a steady speed, and then you'll be able to tell. Now you feel the increased resistance, right? Yeah. Okay, give it your best shot once more. Okay, cool. Now you know what it takes to actually generate the power.
Yeah.
So down at the generating station, there are little hamsters in cages doing this. This is a lot of hamsters, right? Okay, you can hop off. Excellent job. Thank you, Nicholas. I appreciate it. Jason? Anybody else want to feel in their body what the power is to make 100 watts? Okay, so you know the bicyclists doing all their stuff? The Tour de France kind of guys and things like that. What kind of power are they generating? Around 400 watts, right? All day long? No. But a pretty good clip. It's hard for people to do more than a couple hundred watts. It's very hard to do that. And so, let's see, Jenny, I think, was, Jenny? No, who was the first bike rider? Lauren. So, Lauren, it was hard to provide enough light for Jenny to, Jenny was reading, right?
Yeah.
It was hard to provide enough light for Jenny to even read her notes, wasn't it? Look at the power we've got coming here. That's incredible, isn't it? What is the source of that energy? Do you know? Where's that energy coming from?
Many voters.
Hydrocarbons. Burning hydrocarbons is providing most of it. Hydrocarbons, that's a polite way of saying various forms of oil, right? Coal and petroleum, 80% roughly speaking. Take it away, and we're back to Lauren pedaling for Jenny to study at night. So the electricity allows for one thing that's an absolute miracle. It allows you to control the length of the day. You can have light at night, right? You didn't used to be able to. And if we didn't have all those burning hydrocarbons, you will not have all this electric light. Okay, so live in fear. Okay? There's going to have to be something that happens. And the all-electric car we've seen really just has the hydrocarbons around the corner where you don't see. They're still getting burned. So that didn't solve it, right? How about solar power? Kilowatt per square meter, I'm sorry folks, that is not going to save the planet. Okay, unless there are far fewer people. Okay, another idea?
I was just going to say, how many years do you think we have left for our hydrocarbon source?
How many years do we have left for hydrocarbon? That's an interesting question, isn't it? One I will not have to face.
Will we have to face it?
It is conceivable in your generation you will have to face it. It's conceivable. I'm not trying to fearmonger at all in the slightest, okay? But the hydrocarbon consumption on the planet may rise a factor of 10 from what it is now. The United States is using 25-30% of the world's electricity and hydrocarbons. But China has now come up and has matched us. But they have 4 times as many people. They've only matched it for 1/4 of their population's usage so far. And India, what about India? 3 to 4 times our population also. Yeah, we're not even including Europe and Africa in this, right? So if the hydrocarbon consumption rate increases dramatically, then the amount that gets pulled out of the ground has to increase dramatically, and the Earth is going to be empty after a bit, right? When, I don't know. But the use of hydrocarbons in substantial quantities is only about 110, 120 years on the entire history of the planet. It's not been a long time. But it did cause farm production to quadruple in its yield per acre and the ability to live away from the farm. You guys will need to cope with vast changes in social structure if we run out of hydrocarbons abruptly. Humans are very, very creative. Look at the light we've got here. Humans are very creative, typically in times of crisis. And we don't have a crisis yet, but it may happen in your lifetime. It'll be interesting. So like I said, when we did the earlier calculations, I think hydrocarbons and water will be the biggest issues of your generation for coping with. Okay, let's see. What other demo stuff? Maybe we should write some more equations. What do you think? Oh, let me check my electromagnetic device to see what the clock says. 9:12. We have 8 minutes remaining, or roughly 2.5 pi minutes. Okay, so we need to, this chapter is full of equations, isn't it? Full of equations. So the integral. This is this new chalk. Hit that. The integral of the electric field around a loop, a closed loop, is going to be related to this changing magnetic flux. This is what we've been observing. And this is the enclosed flux. So this integral says a closed integral. We look here and it says around the path. So if you look at all the demonstrations, I think all of them, or most of them at least, of the demonstrations, it's the path around the coil that we might want to think about. An electric field was generated in the wire around the coil that went 2 pi r around the coil. And if we had 3,250 coils, it could do this 3,250 times. And it changed the magnetic flux in each coil, causes an electric field on each coil. Now, if I walk from here up the stairs, over, back down the stairs to here, I arrive at the same gravitational potential, don't I? It's a conservative field, and I arrive back at the same potential. However, with the closed loop, here's the closed loop. When you go around, there's an electric field pushing around. You go around and come back to the same point, you do not arrive at the same potential. The electric field is pushing here. You go around, you go around, you go around, you're continuously changing. This is a non-conservative action. It is not going back around to the same potential. So it's the electric field that's pushing is the way you need to think about it, and there isn't a zero in potential to go up from and then back to. So this is Faraday's law. And we have then also Ampere's law equals mu naught I enclosed. So the interpretation physically for Ampere's law was currents make magnetic fields. And we had for vacuum, we have the integral of E dot ds is Q over epsilon naught, the enclosed charge. So charges make electric fields. But we did not find any magnetic charges yet. So we don't have an equation there that says magnetic charges make magnetic fields. We do have here that time-changing magnetic fields make electric fields. So there are two ways in these equations so far to make electric fields. Electric charges make electric fields. Time-changing magnetic fields make electric fields. So we have two sources. These equations are almost complete, but not quite. So we're going to have an additional term to add to these equations. So when we add that last term, we're going to have a full set. This thing was contributed by Michael Faraday. Michael Faraday's main way of teaching science to himself and to the general public was by demonstrations. The empirical basis of physics was what drove him. He did exactly these kind of demonstrations. He was not so good with the math, but he was very good at the voice of nature talking to him. And as a result, he came up with this equation. There's somebody who follows along who was very good with the math as well as the experiments. And we found this guy once already when we were doing the statistical physics stuff, and we wrote the distribution function and called it a Maxwellian. So James Clerk Maxwell, this Scottish guy, made an additional contribution here. He understood Faraday's experiments and could write the math and figured out how to write this math. And he added an additional term that we're going to add here. Ampere's law is incomplete. There's an additional term we're going to add, maybe tomorrow, maybe on Monday, to add to that. And James Clerk Maxwell's addition of that term describes how light works. The light rays, light waves travel, and how radiation, electromagnetic radiation, travels all around. Okay, now, this chapter that we just did all these demonstrations for is very full of equations. The purpose of these demonstrations was to show you the heart of that chapter. If you think about what pushes a charge and how these interactions happen, all of those equations come from what you saw here today. So I want you, when you're studying tonight, to think about, okay, what did I see? Let that voice talk to you, okay? Come on down and try the coils and stuff here now. And you can ride the bicycle as well. Those folks, Kevin, whoever rode the bicycles, they feel now what 100 watts is. Come on down and do it.